Hello everyone, here we'll be discussing chapter 5.4, which is a discussion on the indefinite integral and the what is called the net change theorem. The net change theorem is actually just an application of the second part of the fundamental theorem of calculus, which we'll talk about a little bit at the end, but mainly the focus of this section is to discuss and introduce the indefinite integral. Now the indefinite integral, unlike the definite integral, doesn't have limits of integration. So those are missing here. So recall that from the fundamental theorem of calculus part 2, the definite integral from a to b of f(x) dx, of course, represents the area under the curve of f between the x values a and b. So this shaded region is defined to be the integral, and that's what it represents. So this value represents the area under the curve of this region. And the way we find the actual area using FTC, part 2, is by taking an antiderivative of f, which we call capital F, which I mentioned before is kind of bad notation, and we'll kind of see that this is a better notation later on. Well, right now actually. And then evaluate that between the limits b and a. Mainly we'll plug in the top one minus plug in the bottom one. Now here f, capital F of x, is an antiderivative. So it's not the most general antiderivative for FTC as it turns out, it's just an antiderivative of f of x. And that's only for FTC. Okay, now an indefinite integral, when you don't have limits, so notice here there are limits missing for indefinite integrals, the indefinite integral of f of x dx is just, well, the most general antiderivative of f of x. So here we need to write plus c. In fact, I'll write it here. Even though we're considering this to already be the most general, I just want us to get used to writing plus c anyways. So if capital F of x is already the most general, then it would kind of already include a plus c on its own right. So this c would be 0, I guess. But it's still safe to write plus c at the very end no matter what. And we'll see that with a few of these examples. But notice for FTC part 2, we don't actually need to do that to evaluate these integrals. We don't have to write plus c, that is. And the reason being is because if the antiderivative of this is some function plus c, when you evaluate at a and b, the c is constant, and since we're subtracting, we're going to get c minus c anyways, which will cancel out. So here we don't need plus c because they cancel out, so we just need an antiderivative. But here we need the most general because this is the definition of the indefinite integral. So indefinite integral is our new notation now for antiderivative instead of this terrible capitalization notation. So here we're going to evaluate a few of these just by taking the antiderivative of the integrand. Now remember, the integrand is what is in between the integral symbol and the d variable symbol. In fact, I may have mentioned this before, this is called differential. So in between the integral and differential is our integrand, and we're going to be taking the antiderivative of that integrand. So here the antiderivative of this is 1/3 x cubed, or x cubed over 3, plus a constant c, and that's it for that one. Antiderivative of sine, as we've seen before, is negative cosine. It's of theta, because our differentials with respect to theta as well, plus some constant c, and that's it for that one. So now you kind of see that really what we're doing is just redoing 4.9 really, but now instead of arrows with AD or the capital F notation, we'll be using this integral notation. So the next board I'm going to write out for us will literally just be the list we saw from 4.9, but now with our new notation of indefinite integrals. All right, here we go. So we have a list here of antiderivatives with our new notation of integral, and there's actually a little bit more here than I've shown you in 4.9. So if you want to compare, you can go back and do that, I guess, if you'd like. But anyways, let's just get right to it, and I'm going to show, first off, for these first two, that are just these properties, that this one is that a constant times a function, you can pull the constant out of the integral. So it's the constant times f of x inside the integral. The integral of the sum is the sum of the integrals, integral of f of x dx plus the integral of g of x dx. And I may need to border this off a bit like that. So I hope that's not too bad. Okay. Antiderivative of a constant is a constant times x plus c. So again, this plus c part we have to get used to. We're going to basically write plus c for all of these. We did it for these ones because these are kind of properties. We didn't even get rid of the integral part, basically. So when you get rid of the integral, you write plus c. In fact, the phrasing I always use is if you're integral free, you write plus c. So it even kind of rhymes. So that kind of helps, I think. Now we can check that derivative of kx is for sure just k, because that's the derivative rule for a constant times variable. Just get rid of the constant, or get rid of the variable, I should say. Keep the constant. But not this one, because it's a constant term, its derivative is 0. Power rule, but anti-power rule, is x to the n plus 1 over n plus 1, which I very often write as 1 over that times x to that power, which I think is a better way of writing it, but this works as well. Don't forget plus c. Antiderivative of e to the x is itself, plus c. Antiderivative of b to the x, this one's kind of new. It's itself, but then we have to divide by ln of the base. And the reason why this is true is because notice derivative of b to the x is itself times ln of the base, so the ln of the base multiplied by 1 over ln of the base cancel, and you just get b to the x inside of the integral. So again, taking derivative of this will leave you with the integrand only, so it checks out after taking derivative. Antiderivative of 1 over x is ln of absolute value of x. Remember that for these we write absolute value inside the ln, because a natural log, in fact any log really with any base, can only be taken of a positive number, not of a negative number. But since the reciprocal of x can be negative, or x can be negative that is, then we have to ensure that we do not have a negative inside of the natural log. So long story short, when you take antiderivative of 1 over x, it's ln of absolute value of x technically. Unless x is given to be positive, then you don't need the absolute values. Antiderivative of sine is negative cosine, we just saw that one, plus c. Antiderivative of cosine is positive sine, plus c. Antiderivative of secant squared is tangent of x, plus c. And again, all of these are true because their derivatives are the integrand. Now, what function has derivative secant tangent? That's just secant. The next ones are a little funny, but they're non-co counterparts, but negative. So the antiderivative of cosecant squared is negative whatever the antiderivative of secant squared was, but with a co. So the antiderivative of secant squared is tangent, antiderivative of cosecant squared is negative cotangent. And this is of course true because the way we find the derivatives of those, well, there's this very similar rule in reverse, that since derivative of tangent is secant squared, then the derivative of cotangent is negative cosecant squared. So that means its antiderivative of cosecant will be negative cotangent, because derivative of negative cotangent will be a double negative cosecant squared, which is positive cosecant squared. Very similarly, the antiderivative of this is negative cosecant of x plus a constant c. Antiderivative of this, we've seen this one before, hopefully we remember. It's arctangent or tangent inverse of x plus c. This one you may need to think about and kind of look back at our derivative rules, but this is sine inverse of x. Now the one I'm missing here is, well, cosine inverse. But as it turns out, cosine inverse has derivative negative 1 over this. So it's really negative this. So it's kind of funny, but with that being said, if you pull out the negative, you just get negative sine inverse. So that may be something you want to investigate to see why that's the case. Because it kind of makes it seem like one's a constant plus another. Well, kind of, because it's negative that. So there is some relationship there we could talk about, but that's obviously going a little bit on a tangent. No pun intended, obviously. And you know what? Let's take a look at some specific examples. I'm just going to do 2. This is really generally what's going on, so you can use these to kind of go over any examples on your own. But I'm going to do 2 just to be safe, and then we'll talk about the net change theorem finally. All right, so yeah, I said 2, but we're actually going to do 3. My indecisiveness, I know, shows sometimes. But believe me, it'll be worth it. This one's going to be a little bit of a challenge. We'll talk it through. But for the first one here, notice we have cosine over sine squared. This doesn't appear to be anything that I showed you already, so it's a little misleading. But if you write this in a very specific way, notice this involves trig functions, so maybe it's actually one of those funny ones written in a weird way, and it actually is, because you can write this as cosine over sine times 1 over sine. And notice cosine over sine is the reciprocal of tangent, which is cotangent, and 1 over sine is the reciprocal of sine, which is cosecant. And notice we actually have an antiderivative rule for cotangent times cosecant. It's negative cosecant. So this is actually not too difficult at all. You just need to rewrite it in a way that's more familiar to us, and then we're good to go. So that's really it there. Not too bad. This next one, we can split it up if you want, or we can just take antiderivative of each term and then write a plus c at the very end. I'm going to do that. The only issue is this 3 over this. If it was a 1 over this, then it's tangent inverse. But since it's 3 over, it's going to be 3 tangent inverse. So I'm going to write this. If we antiderive each of these, antiderivative of this is x to the 4 over 4, so it's going to be 2 over 4, minus, this is x to the 1, so after taking antiderivative, it's x to the 2 over 2, so it's 6 over 2 in front. And really remember that this is the same as 3 times 1 over that. So if we split the integral up, we can pull that 3 outside. In other words, the constant multiple doesn't really matter. So it's going to be 3 times the antiderivative of this guy, which is just tangent inverse, as we just spoke of previously. And then we write plus c, and we're really done. The only thing we should do is simplify. I'm just going to do that here by erasing. 6 over 2 is 3, 2 over 4 is 1/2. So I hope that's not too hard to see, and I'm going to call it a day with that one. Now, this next one, like I said, is a little bit of a challenge, and to be quite honest, this problem is introduced way later on, actually in chapter 7, because it involves this kind of different technique. But there is actually a way of going about this from a more elementary perspective based on just the fact that this is the derivative of some function. So to keep that in mind, there are some hints. The first biggest hint is that the denominator is squared. And what do you notice happens when you have a fraction? You take its derivative. When do you get a denominator squared? Of course, by applying the quotient rule, right? So that means maybe, just maybe, this is something over this without the square. Because by quotient rule, you would get it with the square, but then you have to check that the numerator of the quotient rule indeed agrees with this. The other thing is that this is e to the 2x, not just e to the x. So derivative, remember, of e to the 2x by chain rule is 2e to the 2x. So we'll have to keep that in mind. And also notice we may need to use actually product rule on the top, and that gets a little annoying as well. What I'm going to do, though, as a guess, I'm going to notice that this e to the 2x doesn't really go anywhere. In other words, derivatives of e to the 2x are, again, multiples of e to the 2x, and everything else here involves x. So I'm just going to leave this actually as e to the 2x and go from there. If I need to multiply by x to see what happens, then we'll do that. But the first thing we need to do, of course, is just check by quotient rule. So by quotient rule, so I'm checking this by taking derivative. We have all over the bottom squared, which is what we expect to get here. So that so far matches. Now, derivative of the top, by the way, I said we need to use product rule here, but what I really meant to say was using quotient rule, we may get an x popping out of this. Otherwise, if we don't, we may need to attach an x to make something happen similarly. But anyways, we're taking derivative of this over this. So by quotient rule, it's derivative of the top, regular of the bottom. So notice that's 2e to the 2x times 1 plus 2x minus regular of the top, e to the 2x, times derivative of the bottom, which is just 2. So this is really 2e to the 2x. And notice on the top, they both have 2e to the 2x in common. So if you actually factor that out, 2e to the 2x, what we have left over is from the first term, 1 plus 2x. But then from the second term, we have minus 1. Right? I hope that makes sense. Notice that this is 2e to the 2x times that quantity. The second one is 2e to the 2x times negative 1, technically. So if you pull that out, you'll get this. Notice these 1's cancel. Another way to see this, of course, is distributing and combining like terms. You'll still get similar cancellation, though. So notice what we have on top is actually 2 times 2 times x, e to the 2x, all over this quantity squared. And this is actually just, well, it's 4x e to the 2x, all over 1 plus 2x quantity squared. So this actually looks really, really, really promising because we have an x e to the 2x on the top. The only issue is we have that that 4. But since 4 is a constant, that's no issue at all. Because if we were to just look at our guess, multiply by 1 over 4, its derivative will be what? It will be 1 over 4 times that. So we're kind of modifying this as we need, as needed basically. So we get 1 over 4 times this, which is 1 over 4 times this. These cancel, and then it checks out, and boom, we're done. So that means the answer is really this, 1/4 times that. And to clean it up a bit, I'll multiply 4 in the denominator. So I'll write 4 times a quantity like that. I could just leave the 1/4 on the outside, but that's okay. And also notice, what am I missing? What am I missing? I'm missing plus c. So do not forget the plus c. So this is our guess, and then from here we can just formalize this and write plus c. So let me write that here. And we verify this is indeed the case by taking derivative and checking. Awesome. So again, that was a thinker, that was something that's not on the list, but we can kind of make an educated guess based on our knowledge of derivatives and then modify things as needed. So I think that's nice. Now I'll tell you right now that generally you won't have to do any crazy exploring like that, but it's nice to know that you can always check your answer for indefinite integrals by taking the derivative of your supposed answer, making sure it checks out with the integrand. Alright, so finally we have here the net change theorem, and it says the integral of a rate of change is the net change, integral from a to b of f prime of x, notice that represents a rate of change, is the net change of the function itself, whose rate of change is given, f prime. So if the rate of change is f prime, then the original function f, the net change is just, again, just the difference of the values of that particular function at those given endpoints. Now I know it sounds a little general here, it's kind of broad, but really this is just a retelling of the second part of the fundamental theorem of calculus. Now for velocity, so this is a very particular instance, the integral from a to b of vt, where that's a velocity function of t, dt, represents displacement, which is net change in distance. So this would literally be delta x if you are into physics and you've seen that before. But the integral from a to b of the absolute value of v of t, notice velocity could be positive or negative, that depends on direction. But for absolute value, you're kind of changing things so that you're only going one way and not going back and forth. So you're actually tracking the total distance you've traveled. So the integral of the absolute value of velocity would be the total distance traveled. In fact, this idea is really true to capture the entire area without considering negative areas. So if we have a function v of t like this, notice that the shaded region, of course, is going to be this. So notice here we have some positive areas, we have some negative areas possibly, and then positive. Good. But the absolute value of a function, and I say for v of t, but this is true for any function really, is just basically lifting up all of the negative parts now to be positive. And that's really all it is. If you want to take the absolute value of any function, your favorite function, it literally does that. It just grabs whatever's down below and just reflects it over the x-axis. Which makes sense because every negative value becomes positive for absolute values. So now these are all positive. Now again, what these areas represent are the net change of the antiderivative of velocity. Velocity is the rate of change of distance, so this is going to be the net change of distance for each one, but since it's always positive, then that means this will be the total distance traveled, basically. So here we kind of imagine velocity positive, negative, positive, meaning we're going forward, backwards, forward, but here we're only going forward, so we're just looking at the total distance now. So now I'm going to erase this and do one example. It's going to be 2 parts, but it'll only be one example, and then that'll be it finally for 5.4. Alright, so here we have, again, a particular example of what we just discussed. In this case, it's a particle that moves along a line, but that doesn't really matter. What matters is that the velocity is given by this function, t squared minus t minus 6. It's measured in meters per second. So we can only assume that the distance or displacement will be measured in the distance unit, which is meters, because time is in seconds. So we want to find the displacement when t is in between 1 and 4 seconds. And remember, displacement is literally just the integral between 1 and 4 of our velocity function. So this is nothing but the integral from 1 to 4 of v of t dt, which is the integral from 1 to 4 of t squared minus t minus 6 dt. And again, this is a definite integral, so we take the antiderivative of the integrand, which is going to be 1/3 t cubed minus 1/2 t squared minus 6t, and then evaluate this between 1 and 4. And I guess we can just do this real quick in some space I have here. When you plug in 4, notice 4 cubed over 3 is going to be 64 over 3. Minus 4 squared over 2 is 16 over 2, so it's 8. Minus 6 times 4 is 24. So those actually combine to 32, or negative 32. And then minus, when you plug in 1, the t's just kind of go away and you look at the coefficients only. So we literally just get 1/3 minus 1/2 minus 1/6. And let's see if we can evaluate this. I'm going to evaluate it here and then erase my scratch work and just write the answer if that's okay. So here, notice this is negative 32 like we mentioned. If we distribute the negative, we get minus 1/3 plus 1/2 and then plus 1/6. The 64 over 3 and the negative 1/3 combine to 63 over 3, the 64 minus 163. 63 divided by 3 is actually just 21. So we'll end up with 21, and I guess we could do the plus 6 part first. So plus 6, then minus 32, and then we have that plus 1/2 after the fact. Now, 21 plus 6 is of course 27. 27 minus 32 is negative 5, and then negative 5 plus 1/2 is negative 4.5, which is negative 9/2. So this is negative 9/2 or negative 4.5 meters. So I'll write negative 4.5 meters. I'm using decimal here just because it's a little more practical in the context of physics. So again, it's a negative displacement, but that just means we moved backwards overall. So more than anything, the velocity is going to be negative within this region, or within this period, I should say. So now for part B, we want to find the total distance traveled during this period. And to do that, we'll be doing the same thing, only we need to take the integral of the absolute value. That's going to be a little challenging, so let me erase this and figure that out right now. All right, so I've erased the scratch work, and like I said, to find the total distance, we want to take the integral from 1 to 4, same time period, of the absolute value of v of t dt. Now, basically, we want to find where the function is negative and where it's positive. And we're basically kind of given that it's mostly negative because we have a negative displacement. So kind of keep that in mind. That'll, I think, help a little bit. But now, actually, to find out where it's positive or where it's negative, we kind of need to solve this inequality here. And to do that, we'll consider what v of t actually is. Notice it's t squared minus t minus 6. And luckily for us, this can actually be factored. And it factors as t minus 3 times t plus 2. So let's see, we're kind of looking at, and in fact it's best to kind of graph this just to see what's going on. And in fact, notice that if you were to just literally set this equal to 0 and set each factor equal to 0, we get that this is 0 at time negative 2 and time positive 3. If you can only consider positive time, then this negative 2 isn't really a thing at all. But regardless, notice that this equation here is a parabola. The graph of this function is a parabola. It's a facing upward parabola because it's positive in front of t squared, and it passes through these x-intercepts, or I guess t-intercepts. So it looks like this. So for sure, between 1 and 3, it's actually negative, and between 1 and 4, or not 1 and 4, between 3 and 4, I should say, it's positive. So there we go. Look, we even see that it looks mostly negative like I mentioned earlier. So from 1 to 3, it's actually negative, but from 3 to 4, it's positive. So when we take the absolute value, the 1 to 3 part will actually be lifted up. So what this really means is if we take the integral from 1 to 3, we'll get a negative value, but we're taking the absolute value of that so that it'll be positive, and then we'll take the integral from 3 to 4. So we're going to have to split this up actually to perform this integral. So to do that, again, I'm going to split the integral up from 1 to 3, and then from 3 to 4. So that's a v of t. Now it's going to result in a negative value, and we want to take the absolute value of this so that we have a positive value, and then plus the integral from 3 to 4, which will already be positive based on our graph, so we don't need to worry about taking the absolute value of that. So we're kind of doing two integrals, but the good news is we already know the indefinite integral is, well, this expression here. So we actually kind of already did some evaluation, but now we have to do two different evaluations kind of. Basically, we need to plug in 4 and 1, which we did, but we also now need to plug in 3. So really, if we plug in 3 into this, we'll be set. So I'm actually going to try to do that. So let's plug in 3 into this, and that'll be the top value here. So for the first guy, it's going to have to be the absolute value of, when you evaluate that at 3, I'll kind of do it in my head a little bit. 3 cubed is 27 over 3 is 9. Minus 3 squared is 9 over 2 is 9 halves. And then minus 6 times 3 is going to be 18. So that's the first evaluation, that's plugging in 3. And in fact, it wouldn't hurt to actually evaluate this on its own. Notice that 9 minus 9 halves is just 9 halves itself. Or actually, maybe it's better we can just do 9 minus 18. 9 minus 18 is negative 9. But negative 9, notice, is just the same as negative 18 over 2. So that these actually combine as negative 27 over 2. So negative 27 over 2 is the velocity evaluated at 3. Well, not the velocity evaluated at 3, but the integral of the velocity evaluated at 3. So the distance basically evaluated at 3. So now minus plugging in 1. Well, we already plugged in 1 and we got this guy, which is 1/3 minus 1/2 minus 1/6. Notice 1/3 minus 1/2. If you do that crisscross pattern of subtracting fractions, it's 2 minus 3, which is negative 1 over 3 times 2 is 6. So it's going to be negative 1/6, but then minus 6 now. 6 is 36 over 6. So again, there's a lot of arithmetic here, but it ends up being negative 37 over 6. Perfect. And if you combine these, notice it's double negative. So we get positive. Perfect. And notice when you actually combine these, we indeed get a negative value. It's kind of hard to see at this rate, but if you multiply top and bottom by 3 to get a common denominator, 3 times 27 is 81. So it's going to be negative 81 plus 37, which is indeed negative. So that's good that we get negative, because then we can take its absolute value and make it positive. So now for this second guy here, this will be a little easier to do because we don't need absolute values. We're going to take the antiderivative, we're going to get this guy here. We're going to plug in 4, which we did over here. So that's 64 over 3 minus, remember that these two combine to 32. So that's the first evaluation, minus the second evaluation, which is plugging in 3 into the antiderivative, which we just did. And we got negative 27 over 2. So notice here, by the fundamental theorem of calculus, it is plugging in the top one to the antiderivative, not to the function, but to its antiderivative, minus plugging in the bottom one. When you plug in the bottom one, you get a negative, but since this minus is from FTC itself, we get a double negative, so keep that in mind. So with that being said, we can do some evaluation. Of course, this is positive. We don't need the parentheses at this rate. So now I can combine these. I said this earlier was a negative 81 over 6 by multiplying top and bottom by 3. Now let's see, 81 minus 37 is going to be, I believe that's 43. No, 44, it's 44. So this is going to be negative 44 over 6, but when you take its absolute value, it's positive 44 over 6. But 44 over 6 actually reduces to 22 over 3 by dividing by 2. I know I'm kind of going a little quick here. And then we're going to actually add this, which is nice. So we're going to add this one. Let's do that better, because that has the over 3 part. Minus 32 plus 27 over 2. Let's write this negative 32, if you don't mind, as negative 64 over 2. Now we can combine those. And I think it's looking okay. It still looks a little funny, but that's fine. Let me see here. Okay, so this was negative. Remember, this thing should be positive in total. It still sounds a little funny, but I think it will be positive in total. I'm trying to think, like 64 over 3, 63 over 3 is 21. 27 over 2 is 13.5 plus 21 is 34 or something. So this ends up being positive, actually. It's small, but it's small positive, which we kind of knew that would be. We figured that would be based on a graph. So now, again, this is just arithmetic. So adding these together, we get 86. over 3. 86, can that be divided by 3? I don't think it can, unfortunately. But I'll just write it as 86 over 3. Okay? And these, if you combine these, you'll get a negative value. Yeah, remember that 32 was 64 over 2, so that's good. Now, what's 64 minus 27? That's 37. So this is going to be minus 37 over 2. Now, if we want to get a common denominator, yeah, we'll have to multiply by 2. It's kind of ugly looking, but I think it works still. So let's see, 86 times 2, let me do that over here. That's going to be 16, sorry, not 16, 4. Let's see, 2 times 80 is 160, and then 2 times 6 is 12, so that's going to be 172. There we go. 3 times 37 is actually going to be 111. So this is going to be that minus 111 all over 6, because 2 times 3 is 6 for the common denominator. So it's going to be all over 6, and 72 minus 11 is just, well, 61. So it's 61 over 6, or if you want to approximate this, it's about, well, it's 60 and 1/6, well, 60 over 6 and 1/6. 60 over 6 is 10, so this is 10 and 1/6, or 10.17 if you round. And that's going to be in meters. Awesome. Great, so I went a little off screen, but you can see it hopefully. And yeah, that was a little bit of a doozy. It took a little longer than I'd like it to, but at least we saw that application of the fundamental theorem of calculus. And it obviously it still relates to the indefinite integral because we're taking the antiderivative, and then just notice we're plugging in values. So a lot of this obviously has antiderivative written all over it. So it's in your best interest to go back at 4.9, practice those problems. Basically, you'll be doing them anyways in 5.4, specifically with the indefinite integral problems that are going to be asked of you to complete. So again, that's all I want to say for 5.4. The next section, 5.5, is basically concerned with a technique to find the antiderivative or integral of particular types of functions where you can kind of pull this trick off that essentially is the opposite of chain rule. It kind of undoes chain rule. I don't want to say it is the anti-chain rule, but kind of. It's more of a technique than a rule. It's called substitution rule. It's going to be a lot of fun. So I'll see you in the video for that, 5.5. Hope you enjoyed this. I know I did, of course. So I'll see you in the video for that. Thanks for watching. See you then.